In this short series of videos, you will learn how to calculate the crack widths in reinforced concrete structures. The series of videos are all based on the book Structural Design from First Principles, Chapter 10, Control of Cracking in Reinforced Concrete. In this worked example, we're going to consider a basement slab of a building, and the basement slab is cast in one section and restrained from shrinkage due to the pile walls that surround the slab. You need to determine the maximum reinforcement spacing to control cracking if 12mm rebars are used. Heat of hydration is expected to cause the temperature to increase to 35 degrees centigrade before falling back to an ambient temperature of 15 degrees C after 3 days. Calculate the crack width due to the fall in temperature. And the final part says that drying shrinkage strain of 80 microstrain is expected over 2 years after casting. So calculate the final crack width. So the guiding principle for working out the minimum amount of reinforcement in this situation is to make sure that the tensile strength of the concrete is less than the tensile strength of the steel. The tensile strength of the concrete can be quite significant, so we only use the 3-day tensile strength. That's 3 days after casting. On the left hand side here you can see a slab that is cast between two rigid boundaries, and so this is a reasonable approximation of the situation for this design example. Now, if you don't have enough rebar, then a single crack will form. The rebar within that crack will yield because the tensile strength of the rebar is less than the tensile strength of the concrete. Therefore, all further movement will take place in that single crack. And so we will only have one crack form, but it will be a very big crack. If we increase the amount of rebar, then when the first crack forms due to the shrinkage from heat of hydration, then the rebar within that crack will remain elastic, and that will encourage more cracks to form. And so we will end up with more cracks, but each of the cracks will be of a reduced width, and that's the goal in this exercise. So once again, the guiding principle is to make sure that the rebar strength is greater than or equal to the concrete tensile strength 3 days after casting. So the 3-day tensile strength of the concrete is equal to the crushing strength at 28 days divided by 20. Now that's an approximate calculation, but it's a reasonable approximation. And then based on the assumption that we talked about in the previous slide, the minimum area of steel is going to be equal to the area of the concrete. Now the concrete is 290 millimeters thick, and it's, if we consider just a 1000 millimeter wide section of slab, so the area is 290 times 1000 times the tensile strength of the steel, which is 2, divided by 500. So what we need is 1160 millimeters squared per meter, and that can be provided equally top and bottom, and also in both directions. So assuming that we're going to use 12mm diameter rebar, if we use 12mm diameter rebar at 175mm centers, then that will give us 1292 millimeters squared per meter. Now we need to calculate the crack width that we would expect, and to do that we need the reinforcement ratio, so that's the area of steel divided by the area of concrete, and then we can work out the crack spacing using this empirical equation from Eurocode 2. And the crack spacing is 3.4 times the cover plus 3.4 times the rebar diameter. So you can see that if you use a smaller diameter rebar, that will give you a smaller crack spacing, which will also give you a smaller crack width, and then divided by that reinforcement ratio. So approximately the crack spacing is about 1001 millimeters. The free shrinkage strain is calculated as the coefficient of expansion multiplied by the change in temperature. The change in temperature is 20 degrees Celsius. So we'd expect the concrete to shrink by 240 microstrain. In this question, we're going to assume that the restraint factor is 1.0. So we're going to say that the pile walls are effectively rigid and don't allow any movements. So the restrained shrinkage strain is 0.75, which is a factor that was discussed in the previous lecture, multiplied by the free shrinkage strain and the restraint factor. So we end up with 180 microstrain, and the corresponding crack width is going to be simply the crack spacing multiplied by this factor, and we're expecting therefore 0.18 millimeters in the size of the cracks. This is less than 0.2 millimeters, so the crack would probably self-seal with time. The question says that we're expecting 80 microstrain of shrinkage over a 2-year period, so we can recalculate the crack. So this would give us an additional 0.06 millimeters of crack width. So the final crack width was going to come out at about 0.24 millimeters. We did make some fairly conservative assumptions here. We did assume that the restraint factor is 1.0, so this may be a little bit on the conservative side, but it's a reasonable approximation on the final crack width. I hope you enjoyed this short video on the control of cracking in reinforced concrete. There are 6 more videos on this topic available on YouTube, and also in the book Structural Design from First Principles. I hope you enjoyed this, and do press like if you found it useful. Thank you.